Okay, so today we're going to talk about a proof technique called mathematical induction. And I can illustrate this technique, why this is useful, in the following example. So we're just going to look at some experimental data here. So what we're going to do is we're going to look at the sum of the first so many odd integers. Okay, so sums of first so many odd, let's just say natural numbers. So the sum of the first one odd natural numbers, that's just 1. Okay, and let's call this this S1. So S1 is just 1, and that's all there is to it. S2, the first two odd numbers, that's 1 plus 3, and that's 4. S3, the sum of the first three odd natural numbers, is 1 plus 3 plus 5, and that's 4 plus 5 is 9. S4, the sum of the first four odd natural numbers, 1 plus 3 plus 5 plus 7. 1 plus 3 plus 5 is 9. That was our previous step. Plus 7 is 16. And S5, well, that's just our previous one plus 9, and that's 25. And we could keep going like this. S6, that's the previous one plus the next odd, which is 11 in this case. That's the 11th. 11 is the sixth odd number, and that gives us 36. And you can probably see what's sort of going on here is that it seems that if we let Sn denote the, this is going to be equal to the sum of the first n odd naturals. It seems like, so the conjecture, so basically we have a conjecture here. Conjecture is that this is equal to n squared. Okay, because we can see this in the first 6 instances for n equals 1 through 6. We see that the sum of the first 1 through 6 odd natural numbers is indeed equal to 1 squared through 6 squared, respectively. Okay, so to proceed, it helps to just have some notation for this S sub n. So S sub n, so the first odd number, that's 1, and 1 is 2 minus 1. The second odd number is 3, and that's 4 minus 1. That's 2 times 2 minus 1. Then 5 is 2 times 3 minus 1, and 7 is 2 times 4 minus 1. So in general, the nth odd integer is 2n minus 1. So the sum of the first n odd natural numbers is 1 plus ... up through 2n minus 1. And because the nth, so here we're using that the nth odd natural number is 2n minus 1. Okay, so this S sub n as 1 plus 3 plus 5 plus etc. up to 2n minus 1. So our conjecture here is that S sub n, which is 1 plus ... up to 2n minus 1, that's what it is by definition, that's equal to n squared. Okay. So to prove, how to prove the first thought might be that you want to do this directly somehow. So somehow just, directly compute the sum Sn and show it equals n squared. And there is a way to do this, and we won't discuss it at the moment. There is a way to do it this way, but what we're going to do is somewhat more indirect. So the second thought might be to use the fact that we've already established that Sn equals n squared for 1, 2, etc. up through 6. Right? So for n equal 1 through 6, and that there must be some kind of pattern. Well, so we have a feeling that there must be some kind of pattern, so that there must be some kind of pattern or logic that keeps the sequence going. I'm speaking somewhat informally here. Okay, so how we can do that is we know that S1 equals 1 squared, and that S2 equals 2 squared, and right, that S6 equals 6 squared. And to try to sort of uncover the logic that keeps the sequence going, what we're going to do is, and to not get distracted by the details, so what we'll do is look at a case of an n where Sn equals n squared. So we know we have a number of examples of n's such that Sn equals n squared. Right, so suppose that Sn equals n squared for some n. All right, so our n could be 1, 2 through 6 in this. Okay, and what we're going to do is now we're going to look at Sn plus 1. So what's Sn plus 1? Well, by definition, it's 1 plus ... up through, just look at the definition of Sn up here. All right, so you take the last term is 2 times the n, so in this case our n is n plus 1, minus 1. Right, and so just to be a little more clear about this, so you see what's going on. This is just, so I'm going to insert the term before this last term, so the term right here before the plus sign. So you have 2n minus 1, right, and then plus 2 times n plus 1 minus 1. So I'm displaying the last two terms there, and because we'll see that. So you see that this is just Sn here. Right, so Sn plus 1, the sum of the first n plus 1 odd natural numbers, that's the sum of the first n odd natural numbers, and then plus the n plus first odd natural number. So that's kind of obvious, and you can see that in the algebra here. And then we'll just simplify this term here. So this is just 2n plus 1, right? So this is equal to S sub n plus 2n plus 1. I'm just doing a little algebra. And, well, so we're supposing that Sn equals n squared here, right? So supposing that, we have Sn equals n squared, we have the 2n plus 1, and we recognize this, because we're decent at algebra, that this is n plus 1 quantity squared. Right? And so you see that Sn plus 1 is equal to n plus 1 squared. Right? So we went from Sn equals n squared. So if Sn equals n squared, in other words, if the thing we want to prove is true at n, we've shown that it is true at n plus 1. Right? So letting P sub n denote the statement Sn equals n squared, we've shown that P sub n implies P sub n plus 1. Okay. And this allows us to show that all of the S sub n's are true, right? So we're trying to, all of the P sub n's are true. So we're trying to show that this identity here holds for all n, right? So the conjecture here, just to be clear, is that this is true for all n in the natural numbers, right? And so we're just trying to show P sub n for all n. And so I claim that this thing that we've shown here, plus the fact that we've shown a P sub 1 through P sub 6, that those two things together are enough to imply P sub n for all n. And this is the basic logic of induction. So P sub 1, so for example, P sub 1, I'm just sort of drawing a kind of visualization of this. So the statement P sub 1, this is true, right? This is a true statement, because that's just the statement that S sub 1 is equal to 1 squared. And we have that, well, if P sub 1 is true, we know that P sub 1 implies P sub 2, right? So that implies that P sub 2 is true. Now that P sub 2 is true, we have that P sub 2 implies P sub 3, right? So this implies P sub 3, that's true. And this just keeps on going forever. So the fact that we established P sub 1 to be true and established this conditional that if P sub n is true, then P sub n plus 1 is true, is enough to show that P sub n must hold for all n. Right, so thus P sub n must hold for all n. And so the book has a great visual for this. And the basic idea is that you think about each of these propositions here. So the reason I drew them this way, you think about these propositions as being dominoes that are all lined up together. And so one way you can knock down an infinite row of dominoes is you can knock down the first domino and then show that if you knock down any given domino, it knocks down the one after it, right? Because if you can knock down the first one and knocking down the first one knocks down the second one, well then the second one being knocked down knocks down the third, and the third being knocked down knocks down the fourth, and all the way down the line. And so just knocking down the first domino allows you to show that any given domino is going to eventually be knocked down. So that's basically the logic of induction, is that as long as you can show that you can knock down one domino, and knocking down any one implies that the next is knocked down, then all of the dominoes have to eventually fall. Okay, so this is the proof technique of mathematical induction. And so what we have here is that, so this is the general situation. So suppose one wants to prove some statements P sub n for all n in the natural numbers. Then the first thing you do is you prove P1. And this is called the base case of the induction. Okay, so you prove that you can knock down the first domino. And then the second is you prove that P sub n, right, so if you can knock down the nth domino, that's going to knock down the n plus first for any n. Okay, and this is called the inductive step. Okay, and that's really it. So mathematical induction applies when you have this this directed sequence of propositions. So you have a first proposition, and then you have a sequence of them indexed by the natural numbers following that first one. And in order to prove that sequence of propositions, you prove that you can do the first one, and you can show that any given proposition in that line of propositions implies the next one. All right, so that is mathematical induction. So let's write out what a typical mathematical induction proof looks like from the last proposition of that identity we were working with above. So define S sub n to be 1 plus dot 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 plus 2n minus 1 for any natural number. Then S sub n equals n squared for all naturals. Okay, so I mean, we basically did the proof above. We're just going to write it down nicely and to show you what an induction proof looks like. So our proof is by induction. Okay, so we have to do the base case. And so that involves proving the proposition for the first natural number. So for n equals 1, S sub n, that's just equal to 1. And 1 squared equals 1. So we see that S sub 1 equals 1 squared, and the base case is established. Okay, so that's the first domino falling. And the next step is we have to prove this conditional statement. So we're going to assume P sub n. So assume that S sub n equals n squared for some n. Okay, and this is called the inductive hypothesis. So this is called, so when you assume, go to the step of assuming P sub n, then that's called the inductive hypothesis. This is called the inductive hypothesis. Then, well, what do we have to do? We have to prove P sub n plus 1. So we have to look at S sub n plus 1. And that's 1 plus blah, blah, blah. 2 times n plus 1 minus 1. And that's 1 plus, just as before, we look at the term before that last one. Right, and that is equal to S sub n by definition, right? That first, every term with the last one added together, that's S sub n, and then just a little bit of algebra like we did before gives 2n plus 1 is that last term. And this is equal to, well, by the inductive hypothesis, s sub n is equal to n squared. So this is n squared plus 2n plus 1. And again, we remember that's n plus 1 squared. So the inductive step is complete. And thereby, so is the proof. Okay, so that's the logic of induction, and that's the first look at what an induction proof looks like. All right, so we'll do a few more examples just to see that we have the logic of this down. So here's a proposition. If n is an integer and n is greater than or equal to 0, then 5 divides n to the 5th minus, not 5, n to the 5th minus n. Okay, so in this case, notice our n here is over non-negative integers, right? So that's natural numbers together with 0. So in this case, so note, in this case, in this instance, our base case will be p sub 0. Okay, so even though I formulated induction here by saying that n had to be in the natural numbers, really your n could come from any subset of the integers that looks like, so you could replace this with, say, the subset of the integers that starts with a and then goes to a plus 1, a plus 2, etc. So this is a subset of the integers. Right, so you can replace with this subset of the integers, where a is any given integer. Okay, so you don't strictly have to index your propositions by the natural numbers. They might be more naturally indexed by some other subset of the integers of this particular form here. All right, so because the logic of induction is the same, it doesn't depend on necessarily having to start with n equals 1. Okay. So that's the first note there. And I also can't resist noting or remarking that this is a special case. So our proposition is a special case of what's called Fermat's little theorem. And what Fermat's little theorem says is that p divides a to the p minus a for any prime p and integer a. Okay, and it turns out you can actually prove this proposition, this more general proposition, by induction, and it's just a generalization of the induction proof I'm about to give of this proposition. Well, you really need induction and a little bit extra, but it's not that much more difficult. Okay, so maybe some of you want to think about this proposition, how you can prove this proposition here. Basically, you can prove it for a greater than or equal to 0 by induction And then you can use a trick to show that it has to follow for negative a. At least in the case for odd primes, then you can make a different argument for even primes. But that's all. So those are my hints there, if you happen to want to think about that. Okay, so here's the proof of the proposition. So it's by induction. Okay, and so for n equals 0, we clearly have that 5 divides 0 to the 5th minus 0, because that's just 0. Right? So the base case is established. Okay, so now assume that that 5 divides n to the 5th minus n for some n in z, n greater than or equal to 0. Okay, and this is the inductive hypothesis, just to remind you of the terminology again. Okay, so remember, so we're assuming, so this is our p sub n here, and we need to show that p sub n implies p sub n plus 1. So what we have to do is we're going to be looking at whether 5 divides n plus 1 to the 5th minus n plus 1. Okay, so we're going to look at n plus 1 to the 5th minus n plus 1. Compute, or I guess we'll say we compute n plus 1 to the 5th minus n plus 1. That equals, so what we're going to do is we have to do some algebra to compute n plus 1 to the 5th. And there's either a well-known formula you can look up, it follows from what's called the binomial theorem, or you can just do this bit of algebra, just multiply n plus 1 out by itself 5 times. And what you get is the following. So you get n to the 5th plus 5n to the 4th plus 10n to the 3rd plus 10n squared plus 5n plus 1. And then we're subtracting n and 1 from the n there. Okay, and what we know is that 5 divides n to the 5th minus n, right? So what we'll want to do is isolate this term n to the 5th and our minus n here, right? So in the next line we'll write this is equal to n to the 5th minus n. And then we have the 1 and the minus 1 canceling, and everything else is in here, right? So we have plus 5n to the 4th plus 10n cubed plus 10n squared plus 5n. And remember what we're trying to do is we're trying to show that 5 divides this, right? So clearly there's a factor of 5 in every term here that we can pull out, right? And we know that 5 divides n to the 5th minus n, so there must be a factor of 5 in here. And so I probably should have set this up a little bit better, so I'm just going to go back and do that now. So up here, so all I'm going to write here is that n to the 5th minus n must be equal to 5 times k for some integer k. So n to the 5th minus n, I keep doing that, n to the 5th minus n equals 5k for some k in z, and then we compute. So I'll put that line back. So I'm just inserting a new line there. Okay, and now back to the computation, we'll just substitute that in. So we have, so this first term equals 5 times k, and then I'll just pull the 5 out. So we're going to have 5 times k, and then all these other terms have a 5 as well, so I'll pull that 5 out of all of them, plus 2n cubed plus 2n squared plus n. Okay. So we've computed that this expression is 5 times this sum, and so we see that 5 divides n plus 1 to the 5th minus n plus 1. Okay, so we assumed our p sub n, and we proved our p sub n plus 1. So this completes the inductive step and the proof. Okay, so that's our second proof by induction. The next proposition, we'll use the definition of the factorial of a natural number, well, actually a non-negative integer. So recall, or maybe we'll just say definition. If n is a natural number, n factorial is defined to be n times, well, okay, maybe I should say it this way. I'll start counting up. So it's 1 times ... up through n. Right? So it's 1 times 2 times 3 times, etc., all the way up to n. And if n equals 0, then n factorial is just set equal to 1. Okay, so 0 factorial is equal to 1. All right, and here's a proposition about the factorial. If n is a non-negative integer, then the sum from I equals 0 to n of I times I factorial, that's equal to n plus 1 factorial minus 1. Okay, so here's the proof. Wish I knew more about where this identity comes from. I don't. I tried to look it up online and I didn't find any information about it. So if anybody knows anything about that, let me know. All right, so here's the proof by induction. For n equals 0, we have the sum from I equals 0 to 0 of I times I factorial is just 0 times 0 factorial, which is just 0 times 1, and that's 0. So that's that. And on the right-hand side, we have 0 plus 1 factorial minus 1 is 1 factorial minus 1, which is 1 minus 1, which is 0. And so we get 0 on both sides. So we've established the base case. So the base case is established. Okay, now assume that the sum from I equals 0 to n of I times I factorial is equal to n plus 1 factorial minus 1 for sum n. Okay, and again, this is the inductive hypothesis. Then well, what we have to look at is, so this sum with n, that's our p sub n. We're going to look at p sub n plus 1. So we're going to look at the sum from I equals 0 to n plus 1 of I times I factorial. And we want to relate that, so we want to use what we know about p sub n. So we want to use the sum from I equals 0 to n. And the way we can do that is, well, the sum from 0 to n plus 1, that's the sum from 0 to n, and then plus just the last term. So this is the sum from I equals 0 to n of I times I factorial, plus just the final term, which involves the n plus 1. So n plus 1 times n plus 1 factorial. And by the inductive hypothesis, that first sum there is n plus 1 factorial minus 1. So that we have that plus n plus 1 times n plus 1 factorial. And then we group the n plus 1 factorials together. So we have n factorial times n plus 1, and then just n plus 1 factorial. So that would, so you factor that out, you have a plus 1, and then all of that minus 1. And so this is n plus 2 times n plus 1 factorial minus 1. And n plus 2 times n plus 1 factorial, that's n plus 2 times n plus 1 times n minus 1, dot, dot, dot. That's just n plus 2 factorial. Right, and then minus 1. And, well, just to be explicit about this, so the right-hand side of our p sub n plus 1 statement would say n plus 1 factorial minus 1. And that's exactly what we have here. So n plus 2 is just n plus 1 plus 1. So we have that factorial minus 1. Okay, and that is our p sub n plus 1 statement, which completes the inductive step and the proof. Okay. A couple more examples. So here's a proposition. 2 to the n is less than or equal to 2 to the n plus 1 minus 2 to the n minus 1 minus 1. And this holds for all natural numbers n. The proof will be by induction, so we'll give it a go by induction. So the base case for n equals 1 reads 2 is less than or equal to 2 squared minus 1 minus 1, i.e. 2 is less than or equal to 2, which is true. Okay, so that establishes the base case. Now assume 2 to the n is less than or equal to 2 to the n plus 1 minus 2 to the n minus 1 minus 1 for some n. Then, so that's our p sub n. We have to look at p sub n plus 1. So that's going to involve a 2 to the n plus 1 on the left-hand side. Okay? And we want to say that 2 to the n plus 1, that's less than or equal to 2 to the n plus 1 minus 2 to the n plus 1 minus 1 minus 1. Okay, and what we have is the p sub n statement. We have this inequality here involving 2 to the n. So what I'll do is rewrite this 2 to the n plus 1 as 2 times 2 to the n. Right? Actually, I shouldn't say, I mean, that's technically true, but Okay, so first of all, that's equal to that. And then we'll use this inequality here, the inductive hypothesis. And we can say that this, because 2 is positive, we can just multiply both sides of that inequality. We get 2 to the n plus 1 plus 1. That's 2 to the n plus 1 plus 1 minus 2 to the n plus 1 minus 1. Right, so we're just increasing the powers of 2 there, and then minus 2. Okay, this is almost our p to the n plus 1 right-hand side. Right, so the powers of 2 agree. So we have 2 to the n plus 1 plus 1. Oops, that's correct. And we have minus 2 to the n plus 1 minus 1. That's correct. But then we have this minus 2 instead of minus 1. But that's easy to take care of because we can rewrite this. This is 2 to the n plus 1 plus 1 minus 2 to the n plus 1 minus 1. Minus 2 is minus 1 minus 1. Right? So this is the right-hand side we want. And we're subtracting 1 from that, but that's no problem because so when you subtract 1, that's less than, right? So this whole thing here is less than this thing, right? Which is the thing we want. So we can say this is less than or equal to 2 to the n plus 1 plus 1 minus 2 to the n plus 1 minus 1 minus 1. And this is so looking at left here, our left-hand side, that's less than or equal to that right-hand side. That's exactly the statement p sub n plus 1. Okay, so assuming p sub n, we've shown p sub n plus 1. So this, which completes the inductive step and the proof. Okay, so looking at the statement of this proposition, maybe the first thing that occurs to you is to try induction. Right after you've done a few induction proofs, you get sort of hip to the idea that if you're trying to establish something for all n, you should always try induction. It turns out that there's a simpler proof of this proposition that does not use induction. So here's an alternate proof. There's a simple direct proof of this. So 2 to the n less than or equal to 2 to the n plus 1 minus 2 to the n minus 1 minus 1. That's equivalent to 0 is less than or equal to 2 times 2 to the n minus 1/2 times 2 to the n minus 1 minus 2 to the n. And this right-hand side here, that's pulling the 2 to the n's out. This is 2 minus 1/2 minus 1 times 2 to the n minus 1. And that is equal to 1/2 times 2 to the n minus 1. And that is, so which is equivalent to so that's equivalent to just rearranging that inequality. You add the 1 to both sides and then multiply both sides by 2, and you find that that's equivalent to 2 is less than or equal to 2 to the n. And this is clearly true. When n is a natural number. Okay, so just because induction works doesn't mean that it's the quickest way to do things necessarily. So you might be able to find alternate proofs that are more straightforward. Okay, but induction is it's still a useful tool, and it's a good it's a good thing to try in any case if you can't think of something else. Okay. And I think I just have one more proposition, so we're speeding through this pretty nicely. So the next proposition is that if n is a natural number, then for all x in the interval of real numbers from -1 to infinity, the inequality one plus x to the n is greater than or equal to 1 plus n times x holds. Okay. And so what this proposition is saying, it's really something that you might think of more naturally in the context of calculus. So 1 plus x to the n is just the graph of x to the n shifted to the left by 1. So let's see. So what that looks like is basically at -1, it's equal to 0, and then it's this polynomial function like this. And 1 plus n to the x, that's just the that is just this line here. So maybe I'll use a different color. So what this is saying is that, and this is the tangent line to the function 1 plus x to the n at x equals 0. So what this is saying is that this this polynomial function lies above its tangent line when x is between -1 and infinity. Okay. And yeah, so that's all I have to say about that. Okay, so that's sort of clear from the picture, and we could probably make some calculus argument, but there's this more elementary argument you can make just by using induction. So here's the proof. Okay, so so by induction, when n equals 1, the inequality reads 1 plus x is bigger than or equal to 1 plus x for all x in -1 to infinity, which is clearly true. A little bit sloppy there. So the base case is established. Yuck. Okay, and then, so now assume that for some n, 1 plus x to the n is bigger than or equal to 1 plus n times x for all x in -1 to infinity. Then, so that's our piece of n. So piece of n is for all x in -1 to infinity, the inequality with n holds. So now we're going to look at the inequality with n plus 1. So then 1 plus x to the n plus 1, well, that's 1 plus x to the n times 1 plus x. Right? And this is, so piece of n inequality says that 1 plus x to the n is bigger than or equal to 1 plus nx. So this is going to be bigger than or equal to 1 plus nx times 1 plus x. And this is, so right here, so we used that 1 plus x is bigger than 0 since x is bigger than -1, right? Because x is in the interval from -1 to infinity. So x is bigger than -1, so 1 plus x is bigger than 0. Okay, and 1 plus nx times 1 plus x is 1 plus just FOIL. 1 plus x plus nx, which is just 1 plus n plus 1x plus x squared. Or sorry, excuse me. Plus nx squared, right? And that is, well, nx squared is bigger than or equal to 0. So this is bigger than or equal to 1 plus n plus 1 times x. And that is the piece of n plus 1 inequality. 1 plus x to the n plus 1 is bigger than or equal to 1 plus n plus 1 times x. Okay. So the inductive step is complete, and with it, the proof. Okay. So that is how proof, your typical proof by induction works.